Let me share my screen. Do you guys have any doubts in week 6? What about you, Mukesh? Okay, you can see the question properly, right? How about you guys try this and type out the answer in the chat box, or you can unmute yourself and tell me the answer. I'll give you 2 minutes to answer the question, and afterwards I will answer. Okay, 1 megahertz clock is applied to JK flip-flop where J is equal to K is equal to 1. What is the frequency of the flip-flop output signal? So, as you've seen in lecture, when J is equal to K is equal to 1 in a JK flip-flop, the output will toggle, right? And if you have a clock and they're given it's a flip-flop, so you will usually assume it's edge triggered if it's a flip-flop. Level triggered, they'll usually call it a latch. So assuming it's edge triggered, then at every, let's say it's positive edge triggered, then at every positive edge of the clock the output will toggle. So this is the clock signal. Then you mark out the positive edges. We are assuming it's positive edge triggered. You could do it with a negative edge triggering also and get the same answer. So let's say initially the output was at 0. You could start out with a 1 and you would still get the same answer. So we start out with the 0, 0 and at the positive edge the output will flip because J is equal to K is equal to 1. So it will go to state 1. Then it will stay like that until the next positive edge of the clock pulse. At this point of time it will flip again. So it will flip to 0. It's 1. The output will flip to 0. This is the output. This is the clock. Similarly, it will flip state set every positive edge of the clock. So a 1 megahertz clock means that the time period of this is 1 over 10 power 6. So this is the, let's say this time period is t, and frequency is 1 over time period, which is 1 megahertz. That is 10 power 6, or you could say 1000 kilohertz. What about the output signal? You can see that the time period is, if you call it t dash, and then t dash is 2 times of t. So the frequency of the output signal is 1 over the time period of the output signal, which is 1 over 2t. So it's half of 1 over t. So 1 over t is 1000 kilohertz. So it's 1000 by 2 kilohertz, just 500 kilohertz. So that's the frequency of the output signal. Well, a similar question is given here. Here, instead of one flip-flop, there are 3 toggle flip-flops. A toggle flip-flop is nothing but a JK flip-flop where both the inputs are connected to the same thing. So if you have a JK flip-flop, output Q bar, you tie these to the same input and call that input T. So the only 2 possibilities in a toggle flip-flop is if you give T is equal to 0, J and K will be 0. So the output will be the previous state. And if you give T is equal to 1, J and K both will be high. So your output will toggle whenever the clock pulse is given. There will be a clock here. So here, as you can see, all 3 T flip-flops have an input of 1. So whenever an edge occurs in the clock pulse, assuming it's edge triggered, so whenever an edge occurs, the flip-flop will, the output of the flip-flop will toggle. So let's say this is the clock pulse. I'll draw a few more. I want to explain one more concept with the same example. So let's say this is the clock pulse, and let's say it's positive edge triggered. So we'll mark these out. So this clock is given to the first flip-flop. So the first flip-flop will assume it starts at 0. Okay, all the states are initially at 0. The first flip-flop will start toggling at every positive edge. So this is Q1, the output of the first flip-flop. So initially if it was 0, then it will go high at the positive edge, and again it will go low, it will go high, stay the same, and at the positive edge it will go low. So this would be the output of the first flip-flop. So it's similar to what happened here. If we give it to one flip-flop, then the frequency will be half and time period will double. Now the next thing you notice is that for the second flip-flop, the clock is connected to the output of the first flip-flop. So Q1 is the clock for the second flip-flop. So you have to take this Q1 as the clock for Q2. So, and second flip-flop will get triggered at positive edges of Q1. So if you call, since that output is called Q2, if it was at 0, it will flip at the positive edges. Okay, and similarly the output of the second T flip-flop is fed as clock to the third T flip-flop. So what you get is this is taken as clock for the next flip-flop. So initially if Q3 was 0, this will go high, and then at the next positive edge it will go low. So Q2 is the clock pulse for Q3. If you add one more flip-flop, then you could do the same thing. Q3 would be the clock pulse for that one, for the fourth flip-flop. So now you can see at each stage the frequency is getting divided by 2 and time period is getting multiplied by 2. So you start out with the 1 kilohertz clock pulse as they are given, that's 1000 hertz. Q1 will have a frequency of half of that, that will be 500 hertz. Q2 will have a frequency of 250 hertz. So Q3 will have a frequency of 125 hertz. That's option A. Okay. Now one more thing I wanted to explain is this thing will be taught next week, but since these questions are related anyway, so I thought I'll tell it to you. So you can see here that let's say you arrange these bits in order Q3, Q2, Q1, and you say this is your most significant bit MSB, this is your least significant bit LSB. If you see here in the timing diagram, then for up to one clock cycle, so this is one clock cycle, it will go up, stay there for some time, go down, stay there for some time. Here the clock pulse is symmetric, so I haven't drawn it very well, but whatever it is, so you consider the first clock pulse, you see that Q3 is 1, Q2 is 1, Q1 is also 1, so it's 111, that's the number 7, right? And then the next clock pulse, it's 110, that's 6. Next it's 101, that's 5. So you can see 100 is 4, 011 is 3, and then 010 is 2, 001 and 000. So it's counting from 7, 6, 5, 4, 3, 2, 1, 0, and then again it's going to 111. So this type of circuit is called a counter, and since the clocks are different for each of the flip-flops, the triggering happens at different times for different flip-flops. So it's called an asynchronous or asynchronous uh, down counter because it's counting down from 7 to 0, and it's for 3 bits. So it counts from up to 7, so it's called a mod 8 counter. So that's this thing will be taught in your week 7 lectures, but I told you anyway because this question was here. Okay, now suppose you had only one of these flip-flops uh, like this was given in question 2. So the input to the D flip-flop is the complement of your output. So Q bar is even. Let's say we start out with a state 0, 1. Okay, and then a clock pulse arrives. What will happen at the positive edge of the clock pulse? This 1 is the input to the clock, here to the D flip flop, and D flip flop, the output is same as whatever you give to D, right? So this 0 changes to 1, and since this is Q bar, this 1 changes to 0. Now at the next clock pulse, the input is 0. As you can see, this is the input, right? So input is 0. Since input is 0, at the next clock pulse the output will change to 0, and this 0 will change to 1. This keeps on going at every clock pulse, so it's going from 0 to 1 to back to 0, then to 1. So this is similar to this, right? Except that here, instead of counting from 7 to 0, it's counting from 0 to, if you take this as a 1 bit number, 0 to 1, and then 1 to 0. So it's a single bit counter. That's option C. Okay. And one more thing you can notice here is, with 3 flip flops you are able to count 7 numbers, right? You could go from 7 to 0. Or if the clocks were given as negative edge triggered, then it would count from 0 to 7. You'll see all that later. But with 3 flip flops you can count from 0 to 2 power n minus 1. So that means n flip flops you can count from 0 to 2 power n minus 1. So they are asking how many flip-flop circuits are needed to construct a mod 16 counter. Mod 16 is in modular arithmetic. Mod 16 means that your digits vary from 0 to 15, 0, 1, 2 up to 15. So you are counting from 0 to 2 power 4 minus 1. So you need 4 flip-flops. Any doubt so far? Or any general doubt? For people who joined later, if you have any doubts you can ask. Okay. Okay. We'll move on to the next question. The output of the JK flip-flop with asynchronous preset and clear inputs is 1. The output can be changed to 0 with one of the following conditions. So synchronous preset input. Option D is not correct because it's saying you have to apply a synchronous preset input, but the flip-flop has an asynchronous preset and clear. So this is wrong outright. And then, so it must be one of the options A, B, or C, and they're given 3 combinations. Okay, we'll see. So if you draw if you see the truth table for JK flip flop, the next state when J and K both are 0, it'll the next state will be the same as the previous state, so it will act like a memory. When it's 0 1, your output will go to 0. When it's 1 0, it will be 1. When it's 1 1, it will toggle, so you get Q and bar. and you can see that initially asynchronous preset and clear inputs are 1, so they are both disabled, and output has to be changed from 0, it has to be changed to 0. So you can see that if you give 1 0, that is option C, and use a clock, you will get an output 1. So that's not correct. You the next, this is not correct. Option B is you apply j is equal to 1 and k is equal to 1. At that point of time it will toggle, but you don't know what the previous previous output is, right? So if the previous output is 1, of course it will change to 0, but if it is 0, it can go to 1. So you can't be sure that giving j is equal to k is equal to 1 will give you the desired output. Wait, let's see. Well, if you apply 0 1, then you can get your output to 0, but none of the options have a 0 1, right? What do we do? Well, let's see the flip-flop with preset and clear ones. Okay, when preset and clear are both high, they are both disabled. So you can get a 0 either by giving a 0 1, or if you previously had a 0, you can give 0 0, so that will stay as it is. And if you previously had a 1, then you can give 1 1 and it will toggle to 0. And I'm assuming, since I've asked the output can be changed to 0, then they mean that it has to be changed from 1 to 0. Oh, they've already given the input is 1, output is 1. Okay, my bad. Okay, since the output is 1, then only positive out of the options we have is giving 1 1. So it will toggle to 0. If they had given the output was 0 and it had to stay at 0, then we would have to give 0 1. But since output is already 1, then to get a 0, either you can give a 0 1 or you can toggle it by giving 1 1. But since 0 1 is not an option here, then it has to be 1 1. Okay. Yeah, Venkata. Option B is right. It's option B. A feature that distinguishes the JK flip-flop from the SR flip-flop is, what's the difference? A toggle condition. Yeah. Preset can be there in JK and SR both. Type of clock, since they are both flip-flops, they are both edge triggered. Well, even if they hadn't given, yeah, if they had given JK flip-flop and SR latch, then maybe you could say the type of clock is different, because for a flip-flop you give an edge triggering pulse, and for a latch you give a level triggered pulse. But since both are flip-flops, can be the type of clock, and clear input is there in both JK and SR. So one difference is the toggle condition, where the output will toggle. Okay. A 4-bit counter is used to count from 0 to n. What is the value of n? So like I said, if you have n flip-flops, you can count from 0 to 2 power n minus 1. So when they say it's a 4-bit counter, that means there are 4 flip-flops. So you can count from 0 to 15. So it's option B. The straight transition of T flip-flop from 0 to 1 requires. Yeah, I had explained T flip-flop in one of the earlier questions, but I'll explain it again. So a T flip-flop, you can get it by connecting both the J and K inputs of a JK flip-flop to the same input, and you call that T. Uh, Q. So there are only two possibilities. When T is 0, J is equal to K is equal to 0, so Qn plus 1 is equal to Qn, and when T is equal to 1, J and K both are 1, so Qn plus 1 is Qn bar. And this happens when a clock pulse, uh, when the edge of a clock pulse arrives. So from 0 to 1, if you want to transition, then you just need to give 1 as the input to the T flip-flop. As you can see here, if T is equal to 1, then Qn plus 1 is Qn bar, and Qn is 0 as the initial state. So when you give T is equal to 1, it will transition to 1. So 1 at T input. Okay. So here they're given a big circuit, and they've said that point P is stuck at 1. That means regardless of what else is happening in the circuit, this is at logic 1. So if that is 1, the next thing that they're given is both inputs of a NOR gate connected together. That is simply a NOT gate. You can see 1 or 1 complement. 1 or 1 is 1. 1 complement will be 0, so you'll get a 0 here. Then there was a mistake in the diagram. I have corrected it. So it's a NAND gate, and if one of the inputs to a NAND gate is 0, you'll get a high output. So this is 1. And then next you have a NAND gate again. One of the inputs is A, the other input is 1. So its output is A dot 1 complement, which is a bar. So you get a bar here, and similarly uh, after p you had a NOT gate, which is just the inputs of a NOR gate connected together. That's the same thing before F. So that's a NOT gate. So F is a complement, which is nothing but a. That's the idempotent law or some other law. Let's not put that. I don't remember what law it is. Okay. So the correct answer is option D. Alright. A new binary coded pentary number system is proposed, in which every digit of a base 5 number is represented by its corresponding 3-bit binary code. So they're saying the number system has a base of 5. So the digits in the number system, see, for the base 10 number system, decimal number system is base 10, you have 0 to 9, right? Those are the digits. So for a base 5 number system, you'll have 0 to 0, 1, 2, 3, 4, up to 4. Those are the only digits. And when you write a number, say 241, it means in base 5, in base 10, this will be 1 times 5 plus 4 times 5 square plus 2 times 5 cubed will be 5 plus 100 plus 250 or 355. This is in base 10. And this number would be represented by each of the digits would be represented by a 3-bit binary number. So this would be a 010, 100, and 001. So that's how the base 5 number system works. And they're asking us to find the base 5 number if the BCP number is 10001001101. So every digit is represented by a 3-bit number, so you have to group 3 bits, and to the left of the decimal point you have to start from the LSB and go towards the MSB. So you start here for the grouping, and this is 1, 3, 2, and 4. So that's 4, 3, 2, 1. That's option D. Okay, whoever is raise your hands, you can. Oh yeah. So 5 power 0. Venkata, is that the same thing you wanted to say, or is there something else? 71. Okay. Venkata, you have raised your hand. You can ask your question. No? Okay. Okay. The following binary values were applied to the XY inputs of the NAND latch that is shown in the figure in the sequence that is indicated below. So x equals 0, y equals 1, that's the first set of inputs. Then it changes to 0, 0. Then it changes to 1, 1. The corresponding stable PQ outputs will be, okay. Thus, even if you don't know it's a latch, you can do it. You don't need to know about latches to solve this question. PQ X Y. Okay, they give 0, 1 here. What will happen? The one of the inputs to the NAND gate is 0, so you will get a high out the output P. So this will go to 1, and then this is 1 regardless of what happens elsewhere in the circuit. And 1 and 1 is, so P and Y are fed to the second NAND gate. So 1 and 1 is 1, and it's a NAND gate, so it will take the complement of AND. So this is 0. So the first, and you can check that this will be stable. There are no instabilities here. So the first set of outputs is 1, 0, and all options have 1, 0 as the first set of outputs. So we'll check the next set of outputs. Now this is changed to 0 and this is changed to 0. So what will happen? You have output Q is 0. Here let me write the expression. This is Qx complement. This is Py complement. So x is 0, Q is 0, Qx complement is 1. So P will stay at 1. And P is 1. Now Y is 0. So you have Py complement is 1. So this will change to 1. This will stay as 1. Again, since it has changed to 1, we have to check P again. So P is 1 times x is 0. 1 times 0 complement, which is 1. So it's stable now. So this thing stabilizes to 1, 1. And that is not true for what they've given in option A and B. So these two are wrong. But still we have to check two more options. For that we'll have to go to the next set of inputs. So it's going to 1 and this is going to 1. So these are at 1, 1. And both outputs are 1. Both inputs are 1, both outputs are 1 now. So let's say this gate number 2 reacts faster. What will happen is both inputs to gate number 2 are 1, so the output goes to 0. This goes to 0, and then the inputs to gate number 1 are 1 and 0. So the output should be 1. It's already at 1, it will stay at 1. So we'll get 1, 0. Let's say the gate number 1 is faster instead of gate number 2. Then what will happen? Gate number 1 will give you an output of 1 and 1 complement. So this will go to 0. And for gate number 2 it will react slower, so it has the P output has already changed to 0. Q is py complement, which is 0 times 1 complement, which is 1. So it will stay at 1. So it will be 0 or 1. So it can either, the third output state can either be 0 1 or 1 0, depending on which of these uh, NAND gates is faster. So that's shown in option number 3. The output can be 1 0 or 0 1. Any doubts? Okay. They're asking what x is in terms of the inputs. They're asking us to write a Boolean expression. So in previous classes we have seen that for a 4:1 mux, the output is given by S1 bar is 0 bar I0 plus S1 bar is 0 I1 plus S1 is 0 bar I2 plus S1 is 0 I3. That's the output of a 4:1 mux. Let's call this. So for the first mux, what will you get? Y is S1 and S0 are A and B here. So you'll get A complement B complement, I0 is 0. And then A complement B, I1 is 1. AB complement I2 is 1. AB I3 is 0. So this turns out to be A bar B plus AB bar. Now X. So S1 is Y for the second mux and S0 is C. So what you get is Y bar, C bar, I0. I0 is 0. So again the inputs are 0 1 1 0. So we can copy from the first expression. So Y bar C 1 plus Y C bar 1 plus Y C 0. So it's Y bar C plus Y C bar, and we substitute for Y in terms of A and B. It's A bar B plus A B bar complement C plus A bar B plus A B bar C bar. This is nothing but AB plus A bar B bar. That you know because A bar B plus AB bar is XOR gate. Complement of that is XNOR gate, and for XNOR gate the output expression is AB plus A bar B bar. So both of them should be low, or both of them should be high, or both of them should be low. Times C plus A bar B plus A B bar C bar. So you'll get A B C plus A bar B bar C plus A bar B C bar plus A B bar C bar. That is, which one is it? Option A. You have A B C plus A bar B bar C plus A bar B C bar plus A B bar C bar. That's option A. Okay, the Boolean expression, whatever they have given there, can be minimized to what is it? You can try and type the answer in the chat box. Well, if you'll just simply have to try out all the options and see if some of one of it matches. But since I know the answer, I'll start from the answer. So observe option D. You have A, B, C bar, D bar. That's the last term is already there directly. You have A bar, B, C, D bar. So the second term is also there. The middle term in option D is B bar, C bar, D. And if you group the first and the last term, that is A bar, B bar, C bar, D, first and the third term. So A bar, A, B bar, C bar, D. These two you group them. The remaining two terms are there in option D as is. You can see that B bar, C bar, D is common to both of them. You'll get B bar, C bar, D into A bar plus A plus whatever this thing will be copied. This is nothing but B bar, C bar, D plus this thing. So it's option D. Yeah, it's option D. Okay, let's see. For the circuit shown in the figure, D has a transition from 0 to 1 after clock changes from 1 to 0. They have given the clock and D both here. They are given the waveform. Assume gate delays to be negligible. Which of the following statement is true? There are four options, but two options have been cut off. They were in different page, so I didn't bother copying that. You don't need the options to answer the question. And knowing the options doesn't really help in this case either way because they are all similar. Okay, this thing, if you observe, it's a SR latch with uh, I think they made a mistake. I think this is probably an NAND gate, so it should be D and D bar being fed. So if you look at just this portion, maybe that's not a purple color. Okay, this is okay. If you look at this portion, this is a circuit of an SR latch where this is S and this is R. So if you are implementing with NOR gates, then uh, the output that is just after S will be Q bar, and the output that is straight from R is Q. If you connect with NAND gates, if you make a circuit, then what is connected directly, it's not connected directly, but what is in line with Q is S bar, and what is in line with Q bar is R. Or if you have R bar, or if you have NOT gates, you can simply give S and R. If you use NOR gates, then you can see in this line you have S and Q bar, here you have R and Q. So most of the time nobody really goes and gives inputs to these things and check what is happening and figure it out. It takes too much time. So you have to remember what type of circuit it is. And which are the inputs and what are the corresponding outputs. So if you mix that up, you might get wrong answers. So if you take this as R and this as S, somehow if you confuse that, then when you're solving, you might get different answers in different questions. You might get the wrong answer. So here, this is S and this is R, and no, it is the opposite. So D is connected to S and D bar is connected to R, so it's a D flip flop. So the bigger portion, this is SR, should say latch instead of flip flop. So latch, and this whole thing is a D latch, I guess. So in a D latch, what will happen if you give D is equal to 0, you will get Q is equal to 0. Q is your output. Q is the output that we consider. Q bar is also an output, but we usually, when we say or the output, we take Q as the output. And when you give 1 to this D, you will get a 1 at the output. But the thing is, this will only happen when the clock input is high. So this transition won't happen if clock input is low. So initially what happens, this clock is high up to this point. So at that time D is 0. So your Q, your output will be at 0, right? And then clock will go low. When clock goes low, the circuit is just disabled. And if it's disabled, it will carry on the previous state that it had. So it will stay at 0. Okay. Is that correct? I'm not sure because I don't have the answer with me for this. Let's see. Well, that's the logic. Give me a minute. I'll think about it. Maybe it's not an AND gate. Maybe both are. Maybe it's just a buffer. Uh, let's just well, only this portion is an SR latch. I was mistaken earlier. So there's one more stage before that. So this portion is an SR latch, and is that right? Let me check the notes. Yeah, only that portion is an SR latch, and this is S and this is R. Okay, and here S is nothing but D plus clock complement, and here it is. If it's an AND gate, then it should be D plus clock complement. So those two will be the same, which might give us invalid combinations. Let's see. Well, I can't think of the correct answer right now. We'll get back to that some other time. I'll check the circuit once. I'm not even sure if the circuit is proper, because usually what happens is the clock and your input are ANDed, right? Is that what happened? Yeah, your enable and your inputs are ANDed. So here they have given a NOR instead of that. So I am not really sure what happens. Uh, Maybe the circuit that they're given is not the right one. So yeah, I think there's a mistake in the circuit. I'm not sure which it is. Whether this is supposed to be NAND gate or whether this is supposed to be NAND gate, because you see, this part is an SR latch, and this is SE, this is your R. So when both the clock and D are high, um is there a portion like that? Okay, there's no portion like that. Okay, consider this portion. The clock is high and your D is low. So at that time, the clock plus D that's being fed to both S and R here, if you consider this as an AND gate. So that is high. So both S and R will be low, and that will preserve your previous memory state. We don't really know what the previous memory state is, so I'm not sure how how they. Okay, let's figure out what will happen in the next part. Where both clock and D are low, the output of the NOR gate is 1 and 1. Again, this input is invalid, right? So that can't really be proper. This would the output would depend on your yeah, Dr. Vijay Kumar, you can go ahead. No, they're saying delays are negligible, right? So yeah, gate delays are negligible. The input itself is yeah, but see, but the what this leads to an invalid input to this, right? So when you get an invalid input, then S and R both are 1 1. This middle portion where both clock and D are low. This portion clock is also low and D is also low. Yeah, they're given clock plus D complement, which will be 1 1. So when they give 1 1, the output will depend on which of the latches acts faster, and also the yeah. So we don't really know what's going to happen. Maybe they meant to say this is complemented. If that is true, initially what will happen? Clock is high and D is low. So clock plus D is 1, and you'll have 0 at S. You'll have a 0 here, and then here you'll have D bar is high, clock is high, so you'll have a 0 here. So that's the previous state. And then when both clock and D are low, this will go to 1, and this will go to 0. This will stay at 0 because D bar is 1. So this will stay at 0. Now you have 1 0 to the SR latch. So yeah, the clock will go to 1. No, the output Q will go to 1 now. So and Q bar will go to 0. And then next clock is low, D is high. So this will go to 0. Uh, this will go to clock is low, D is high for the third part. Clock plus D is high, will go to 0. D bar is also low. So this will go to 1. So this is 0 1. Uh, so this should go to 0 and this should go to 1. It's not staying at any of the. I'll see the other options if they are right. Okay, they have other options. Option C is Q goes to 1 at the clock transition and goes to 0 and D goes to 1. So that would be the right answer, right? Q is in the middle part where clock is going low, so that's the clock transition. Q is actually going to 1. And then When D is transitioning from 0 to 1, that is in the third part, your output Q is going to 0. So that would be the right option, except that this book says that option A is correct. Well, we can't trust the book. First of all, the circuit itself, this is probably a NAND gate. So there's a mistake there itself. So at least from this analysis, it should be at clock transition, Q goes to 1. Why is that? Because at clock transition, both clock and D are 0. So the first NOR gate's output is 1. The second NOR gate, assuming this is D bar as given, second NOR gate's output is 0. So you have a 1-0 combination to this SR latch. So Q will be 1 and Q bar will be 0. And then at D transition, so when D is transitioning, that means in the third part of this waveform, clock is low and D is high. So one of them is low and one of them is high. That will again bring your S and R to 0 and 0. Or wait. So clock and D are low, so the first NOR gate gives you a clock is low, D is high, so the first NOR gate gives you a low, that's this. And then since D is high, D bar is low, so you'll get a 0 here, and clock is also 0, 0 or 0 complement is 1. So R will go to 1. So SR is now 0, 1, and Q will go to 0, Q bar will go to 1. So at least if you assume D is not directly connected, then it's connected through a NAND gate instead of AND gate, then at D transition Q goes to 0. Okay, maybe this is from a previous year CADE paper. It's from 2008 or something. So it's a pretty old paper. Maybe they made a mistake, or maybe the guy who printed the book made a mistake. I'm not sure. At least analysis wise, I hope you understood how you would analyze this thing. Any questions? Anyone has a different idea? Maybe you disagree with the analysis? No? Okay. Did I miss something? I don't think so, but if I miss something, you can voice it out now. Okay. For each of the positive edge triggered JK flip-flop used in the following figure, the propagation delay is delta t. Which of the following waveforms correctly represents the output of Q1? Okay, this is, as you can see, we had discussed similar type of question. Yeah, the circuit itself may be the earlier one. Circuit may be not. Here, let's see. For question number 15, this is like the counter circuit that we saw earlier. So um, clock is given, it's positive edge triggered. So since J0 K0 are 1 in both of the flip-flops, both the flip-flops will toggle at the positive edge of their corresponding clock. You have to observe that both the flip-flops have a different clock. So for the first flip-flop, the clock is given as a waveform here that we have, and for the second flip-flop, clock is the output of the first flip-flop. So let's analyze that. You have this clock pulse here, and it's positive edge triggered. So the first flip flop, it will toggle. Uh, let's assume, since output waveforms all have 0 at the beginning, so we can take it as the output being 0 before anything starts. So it has been preset to 0. So if you start from 0 at the positive edge, it will toggle like this. So this is what is supposed to happen, but they have said that each flip-flop has a delay of delta t. So this is t1. So there's a delay of delta t in this change. So it won't exactly change at that time. So what you'll actually get for q0 is something like this. And here there's a delay of delta t. Now this is the clock for the second flip-flop, and that flip-flop also has a delay. So if there was no delay, you're supposed to get something like this, but there's a delay of delta t. So this thing, it's delayed, and this part is delta t. So if you, in comparison to the actual clock signal, this thing is delayed by, the output of the second flip-flop, it's delayed by 2 delta t from t1. So it can be option B or C, it can be A or D. Next thing you observe is that each stage the clock frequency gets halved. So and the time period gets doubled. So since there are two stages, the time period is 4 times, so it should be 4t. So it's option B. Okay. Uh, I don't have any more questions, but if you want to continue, I'll continue. You guys want to continue? You can do a few more if you are interested. I'll take a washroom break for 2-3 minutes, and when I come back, if people are still there, I'll continue. If you all left, I'll also leave. Okay, if I 2-3 minutes washroom break. You can also go and take a break if you want. There are only three of you here. Do you guys want to continue or do you want to go? If you want to go, you can go. Amit Kumar and Nirala. You guys have to say. If you want me to continue, I will continue. Do you guys want me to solve some more problems or hello? Huh? Hello? Uh okay, fine. Uh See, I need to run this video whether there's content or not for a few more minutes. I'll just pad it with empty space, okay? So you can leave. I'll just leave the meeting as it is. Maybe I'll just do a few more questions just, and you can watch the recording. It'll be uploaded on YouTube. So okay, yeah, okay. I'll solve a few more questions. If somebody is watching this on YouTube, you get bonus questions. Okay. For the circuit shown in the following figure, I0 to I3 are inputs to the 4:1 multiplexer. R is the MSB and S are control bits. R and S are control bits, R is the MSB. That's what they mean. What is the output? So as we had seen previously, Z is R RS I3 plus RS bar I2 plus R bar S I1 plus R bar S bar I0. So I3 is P. This is RSP plus R S bar I2 is PQ. R S bar PQ plus R bar S P plus R bar S bar I0 is P plus Q bar. This is RSP plus rs bar pq plus r bar sp plus r bar s bar p plus r bar s bar q bar. Which of these is the correct answer? We'll have to simplify this. There are 5 terms in each of these expressions, but our outputs have only 3 terms and 4 terms. Let's see. So we can group RSP and R bar SP. So these will give you SP. Let's see. There's no P R bar S bar in the options. None of the options have that term. Now the options have the term PRS also. So you need to eliminate those 2 things. 1, 3 and 4 have Q bar, R bar, S bar. So it could be one of those. PQ S bar R is present in option number 4. So it could be option 4. One thing you can observe is that all these terms have a PQ in them, so we should try to get PQ in all our terms also. So you could write this PQRS plus PQ bar RS plus PQS bar R plus PQSR bar plus PQ bar SR bar plus PQ bar R bar S bar plus PQ R bar S bar. Let's check. So you get PQRS plus PQ bar RS. Fine. Hmm. PQS bar R PQSR bar plus PQ bar SR bar plus PQ bar R bar PQ R bar S bar. Okay, that's all fine. This thing is PQ bar R bar S bar plus P bar Q bar R. Okay, maybe we get a better answer with a K map. We have PQRS, PQ bar RS, PQS bar R, PQ SR bar, PQ bar SR bar, PQ bar R bar S bar, PQ R bar S bar, PQ bar, and did I miss a term? There are 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, and I have only 8, so I missed a term. I have PQRS, I have PQ bar RS, PQ S bar R here, PQ SR bar is here, PQ bar SR bar, PQ bar SR bar is here, PQ bar R bar S bar here, PQ R bar S bar, PQ bar R bar S bar. Okay, this and this are the same term, so we got now this we can form a group. PQ plus E Q bar S. Yes, that would be first option will be PQ plus PQ bar S plus Q bar R bar S bar, uh, which doesn't seem to be right, at least not from the truth table. So it's not first option. PQ bar. So we don't have a PQ bar term. We can't really get that. So it's not this one either. PQ bar R bar. So that we could get from here. P bar QR. That's not really there. So it's not option 3. PQR bar. You can get from here. PQRS bar. That's this one. PQ bar R bar S. That's here. Q bar R bar S bar. That's this and this. So PRS one term is not there. Well, it doesn't seem like any of the options are right. Maybe there was a mistake in forming the question. Maybe. Solution that they have given, they have taken this to be I0, I1, I2, I3. So you can try solving that. Uh, okay. So next question, which of the following Boolean expressions correctly represents the relation between P, Q, R and M1? So X is PQ complement and Y is P plus Q, P or Q. Z is XY, it is P or Q into. This is nothing but P bar plus Q bar. De Morgan's law. So you get p bar, which is 0, plus q bar plus p bar q plus q bar is 0. This is p XOR q, that's z. Now m1 is z XOR r and z is p XOR q. So m1 is p XOR q XOR r is option D. Okay, next question. Two numbers represented in signed 2's complement form are p is 1 1110 1101 and q is 1110 0110. If q is subtracted from p, the value obtained in signed 2's complement form is. So in 2's complement form, p is 1101, which is at a negative number, it's a negative number because most significant bit is 1. So to get the magnitude of this number, you have to do 2's complement again. So 0001 0010 plus 1, which is 0001 0011. That's p. So p is minus this number. Q is 1110 0110. So the 2's complement of this number is 00011001 plus 1, which is 0001 010. So it's a negative number, and q is subtracted from p, so this number is subtracted from p. So you're actually p minus q can be taken as p plus minus of q. So it's actually the negative. Okay, wait a bit. It's actually minus 00010011 plus 00011010, which is nothing but the initial zeros can be taken away. They don't really matter here. If you get a positive number, if you get a negative number, then you'll have to be careful. Okay. So 11010 is larger than 10011. So the output will be a positive number, and in Science 2's complement form, you should get 0 in the MSB. So it should be option B. Without even performing the calculation, you can tell that. Let me verify if that's true. Yeah, it's option B. The logic is that this number is bigger than this number. So your output is a positive number. And if your output is a positive number in sine 2's complement form, the most significant bit is 0. And the only option which has 0 in the MSB is option B. So it should be option B. Let's verify it by doing the subtraction anyway. So 11010 minus 10011, how would you do it? So 0 minus 1 is, you have to borrow 1 from this number. So you have to borrow 1. This will become 0. This will become 10. 10 minus 1 is 1. Again you have a 0 minus 1. So you have to borrow from here. You borrow a 1. So this will become 0. This will become 10. Then from that you borrow a 1. So it will become 1. This will become 10. So 10 minus 1 is 1. 1 minus 0 is 1. 0, 0. The remaining 3 bits were zeros anyway. So that's option B. I'll do 2 more questions. So I'll do all 3 questions. Let's say this 19, 20, 21. Question number 19, x is equal to 1 in the logarithmic equation, and x plus z into y bar plus z bar plus xy bar times x bar plus z bar into x plus y is 1. So since x is 1, the first expression is, so they're given in question number 19 x is equal to 1, and we have to figure out some condition. Condition x plus z into y bar plus z bar plus xy bar into x bar plus z bar into x plus y is equal to 1. Now since x is equal to 1, this is 1, and 1 plus anything is 1. So this entire first term is 1. So you'll get 1 times. Here x bar is 0. 0 plus z bar into, here x is 1. Again 1 plus y is 1. So this thing is 1 is equal to 1. So this is 1 and 0 plus 1 and so anything is uh, that something. So 1 and a is a. So this thing is 0 plus z bar and 0 plus a is a. So this entire thing is z bar. Z bar is equal to 1. That's if z bar is equal to 1, z is equal to 0. So that's option D. Next question is, what are the minimum number of 2:1 multiplexers required to generate a 2 input AND gate and a 2 input XOR gate? So you have the circuit of 2:1 multiplexer is, you have a select line S, you have 2 inputs, this is I0, I1, and let's say this is your output Y. Y is equal to I0 if S is 0, so S bar I0, and Y is equal to I1 if S is 1, so it's S I1. So let's say we want a two input AND gate. What we want is, if inputs are A and B, we want the output is equal to AB. So you can see that here, suppose I give S is equal to A, then Y is S bar I0 plus, sorry, since S is A, this is A bar I0 plus A I1, and then I can give I1 is equal to B, and I0 I can connect it to ground, I can give it as 0. Y is A0 and 0 plus A and B, which is nothing but AB. So with a single multiplexer I could get an AND gate. So it's not any of these options. So it can be option D. And I need a 2 input XOR gate. For a 2 input XOR gate, if your inputs are A and B, you want your output to be A bar B plus A B bar. So let's see. How would you do that? You can do that in a similar way. You give S, this is for and here I'll write for XOR. We can give one of the control inputs as your input. So you'll get Y is A bar I0 plus AI, and you have observe and compare these two expressions, this one and this one. You will get I0 should be B and I1 should be B complement. So you get Y is equal to A bar B plus AB complement. But we don't have B complement. For that we will have to use another multiplexer. This is 1 mux. To get B bar, we need another mux. So how would you do it? You could simply give B as your control input, and if B is 0, you want to get 1, so you can give I0 as 1. If B is 1, you want your output to be 0, so you can give this I1 to be 0. So now you will get Y is B bar 1 plus B is 0, which is nothing but B bar. So you need one multiplexer to get B bar. So in total you need 2 mux to get 10 to get a 2 input XOR gate. So the correct option is 1 and 2. Okay. Final question. Refer to the NAND and NOR latches shown in the figure. The inputs P1, P2 for both the latches are first made 0, 1 and then after a few seconds made 1, 1. The corresponding stable outputs Q1, Q2 are. Okay. First, the inputs are made 0, 1. So let's put this as 0, 1. What will happen in this case? The output of the NAND gate will be 1 and the Q2 will be 1 and 1 whole bar, which will be 0. So it's initially at 1, 0. After a few seconds, this is made 1, 1. So this will be made 1, this will be made 1. So you can see for the NAND gate, first you have 1, 0. So it's not this option. It can't be option A because option A says that NAND gate first has 0, 1. That's not true. Next, when both are changed to 1, 1, you have Q2 and P1 is 0. So you have Q1 is equal to 1. Now 1, 1 complement is 0. So it stays at 1, 0. So it can't be this option either. This goes to 1. This goes to 0. So both of them stay in the same state. Let's see, come to the second circuit, a NOR latch. The inputs are 0 and 1. When inputs are 0 and 1, since input to the second NOR gate, one of the inputs is 1, its output will always be 0. And since both the inputs to the first NOR gate are 0, its output will be 1. So it's initially at 1, 0. That is true in both option B and C. Now this is again changed to 1. This is changed to 1. When both of them are 1, what happens is both the NOR gates will give 0 as the output. So both of these will go to 0. So it should be option C. Okay, option C is correct. Well, that's it for today's session. I'll end the recording now.